Okay, so we're going to look at three resonance structures for a C-deprotonated acetamine, i.e. it's an anion. So which of the following is the correct order of best to worst resonance structures based on the formal charges? So we can see that, and we won't go through this, but you should double check, is that all of these are correct Lewis structures. They all have the right number of electrons, they all have the same number of electrons, and they all satisfy the octet rule around each atom. So our question is, which of these is going to be the most stable of the possible resonance structures? Okay, so what we need to do is look at the formal charges. So let's dive in. Let's start with the center atom. The center atom is the same in all cases. So the center atom is a carbon. It has 4 electrons minus 1/2. 8 electrons in bonds equals 0. So that's great. It's 0 everywhere. That's nice and simple. Now let's start on the left. So we look at the, here we've got a C, and with 2 H's there, that just means carbon bonded to 2 hydrogens with single bonds. And so that's what it looks like there if we draw it out more explicitly. And so there we have, this has a number of electrons of 4. And then we have 2 lone pairs, and then we have 1/2 minus 6 electrons in bonds. And so that gives us a -1. So there's a -1 formal charge there. Up on top, this oxygen. So the oxygen has a valence number of 6, minus 4 electrons in lone pairs, minus 2 electrons in bonds, and that gives us 0. And then the NH2 with a lone pair, remember that's NH, bonded to the carbon 2, so that's 5 minus 5 valence electrons, minus 2 lone pairs, minus 3 electrons in bonds equals 0. So that has a 0 there, that has a 0 there. We've assigned the formal charges for the first molecule. All right, in the second molecule, then the NH2 is the same. We've already done that. That's just 0. Now we've got a new one. That's a carbon with a double bond to the carbon in the center and 2 single bonds to hydrogens. Well, we actually did this case already. It's the same as the central atom. It has 4 bonds. So a valence of 4 minus 4 shared electrons. 4 bonds, 4 minus 1/2, 8 is 0 there. Now this oxygen is different. That has 6, and then minus 6 lone pair electrons, 1/2, 2. That gives us a -1. So this is a -1 here. That just like the first Lewis structure, that satisfies the rules as well, because the sum of the formal charges is the same as the sum of the anion. You always want to check that. Is the sum of formal charges 0 for a neutral molecule, or -1 for -1 anion, just has to add up to the total charge. Okay, let's look at the last one. So this CH2 with 2 lone pairs, we already did that one, that's a -1. Oxygen with 3 lone pairs, with 6 lone pair electrons, 3 lone pairs, that's -1. And the NH2 is new. There it's a N with a double bond, an H and an H. And so we have 5 minus no lone pair electrons, but 1/2 times 8 is 4, plus 1. Plus 1 there. Okay, so we've assigned all the formal charges there, and we can see also, the formal charge assignment works out because the sum is to -1. So what are the rules? Which of these sets of formal charges are more or less stable? Well, let's look at the case on the right first. That has a lot more formal charges. You have 2 -1s and a +1. And by the rules, that's less stable. Qualitatively, why would that be the case? Why do we want fewer formal charges? Well, in this case, you have a large separation of the electrons. Like the oxygen and the carbon are really pulling electrons in one direction, but they're really pulling away from the NH2. And you've got a charge imbalance. You've got a positive part of the molecule and a negative part of the molecule. The electrons just want to come together and not have that charge separation. If you got a big -1 in one place and a +1 in another place, that's they're going to attract each other, and you get lower in energy by moving those charges closer to each other. So this is the worst. That's the worst. All right. So let's look at the other two. Well, the other two actually satisfy that rule. They have the minimum total number of formal charges you can have. You've got a -1 on the oxygen and a -1 in one case and a -1 on the carbon. And that actually goes to the next rule. If there has to be a formal charge, you want the extra electrons on the more electronegative atom, which would be the oxygen. So this would be the best right here. And then this one is middle. The one on the, this one over here, the one on the left is middle. So that one is more stable than the one with separated charges, but less stable than the one where the electron is on the oxygen. So remember, these are resonance structures. These are all valid structures. So it does spend some time, you know, it's a combination of these, but it's not an equal combination. It's more this one, then less this one, and even less this one here. What are the exact numbers for what the combination and how you weight the combination? This is not a high enough level of theory to tell you that. This just tells you, well, you know, whatever the average structure is, it looks a lot more like the one that's labeled best, a lot more like having the excess electrons on the -1 than anything else. And it'll be less of a combination of the others. But really, it's actually pretty impressive that this gives descriptions that match quite well what we see from experiment, despite all we're doing is counting number of valence electrons around. So it's really quite impressive that we can learn this much, given how complex Schrödinger's equation is. Okay, so that's the end of this segment where we've been discussing resonance structures, how to account for the fact that the real structure is actually a combination of the possible valid Lewis structures, and also how to rank those, how to tell in those combinations which ones are the most important, the ones with the best set of formal charges.